Very recently, Hao Hang proved the conjecture called the sensitivity conjecture by using the Cauchy's interlacing theorem. So in this section, I'm going to show you his proof. But let me first describe what the sensitivity conjecture is. Okay, so we start with a Boolean function. So what is a Boolean function? A Boolean function is a function defined on the length n binary sequence to 0, 1. Right? So you can think of some circuit, right? So you have some circuit. What I mean by circuit is like you have like zeros and ones, and you have a gate like AND, or a NOT, and things like that. So by using all these inputs, you output either 0 or 1. So that's a Boolean function. And for any subset S of 1 of 2 and X, which is a 0, 1 vector of length n, or you can think of it as a like length n string, n-bit string, no, n-bit integer. We say we write xs to be with a 0, 1 vector obtained by flipping i's coordinate for all I in S, right? So for instance, if x is like 1, 0, 1 and s is like 1, 2, then xs is like it's going to be 0, 1, 1, right? So this is position for 1, 2, and 3. So you're flipping some bit, and then you get a new data. Then for a Boolean function, f, the local sensitivity as fx is the number of indices I from 1 up to n such that f of x is different from f of x when you flip i's bit, right? So you have some function, some unknown circuit, and you're trying to change the output by flipping one input one at a time, right? So you try like first input, if it was 0, you change it to 1 and see whether the output is different. For the second gate, for the second input, you change to 1, whether you see whether the answer is different. So you try for each one. So you flip it and see whether the output is different. And the number of places where you change, your change makes the output different, then that is the local sensitivity. And then the sensitivity of f we write as SF is the maximum among all n-bit string maximum of f of x. No, s of f of x. So which means that at any state the number of bit flip required to change. I mean, no, the other way around. So for so if the sensitivity is k, that means if you change more than k bits, then the function will definitely change, right? No, oh no, the other way around. If sensitivity is k, that means if you, I mean, at any point, if you change the number of positions you could flip the output is always like at most k. Right. Now, this is a local sensitivity, and then there is something different. So the local block sensitivity PS f of x is the maximum number of blocks, let's say B1, B2, pk of 1 up to n. So blocks are disjoint such that for each pi f of x is different from f of x pi. So you want to group the indices together so that whenever you flip, you're changing the output. So if I have some bits where this thing changes the output, then you can take that as a block, right? So B1, B2. So this means that local block sensitivity of f of x is always greater than or equal to this local sensitivity at x. Right? If you have I many places whose flip changes the output, then you can put each of them as the block. And then the block sensitivity Bs of f is the, again, it's maximum of local block sensitivity. Now here's the conjecture by Nissan and Segedi in 1994, and this is called the sensitivity conjecture. And this conjecture says that for any Boolean function, the block sensitivity is at most sensitivity to certain power for some c. This is true for any Boolean function. And until recently, this conjecture has been widely open. The best bound, best upper bound was due to Kenyon and Kutin, who showed that block sensitivities at most like e to the s sf and square root. I'm not so sure whether this is some exponential. Probably this. I don't remember exactly. It could be wrong. But and the lower bound, there are examples showing that block sensitivity is at least something squared, sensitivity squared. So there was a huge gap. The best upper bound known was like some exponential function, That's the lower bound. That's quadratic function. And then in 2019, Huang came up with a really short and elegant proof by using interlace theorem. And but of course, before that, there was a whole previous research reducing this sensitivity conjecture to a problem on graph theory. So let me explain the reductions. I mean, I'm not gonna show you the proof. I don't even know the proof. But you can imagine that the graph we are talking about will be the cube. So the Qn is graph on 0, 1 to the n, whose edges are the okay, I mean, I should say such that x, y are adjacent if they are different only on one coordinate. So in other words, y is equal to x to the I for some I. Then this is called the hypercube, or sometimes simply called the cube. So Q1 is what? Q1 is this, right? 0, 1. Q2 is square, and Q3 is really a cube. No. So that's the cube. Now, the degree of a Boolean function is the degree of the unique multilinear real polynomials representing f. What I mean is, so for instance, f of x1, x2, xn could be like x1, x2, x3 plus x4 plus 1 minus x5, etc. You can write anything, any Boolean function as a multilinear polynomial. The reason why it's going to be multilinear is because when you have a square, then on 0, 1, you can replace square by linear function, right? x1 squared is equal to x1. The 0 squared is 0, 1 squared is 1. So you can write any function you like, and then you can reduce it. And then it becomes a multilinear polynomial. And this can represent any function because I can write a function that has value 0 everywhere except one point on the cube. Right? So for instance, if I write x1, x2, xn, this is a function that is 1 if the location is 1, 1, 1, 1. And otherwise it's 0. So only and then you take a linear combination of these functions where you replace 1 minus, like instead of x1 you may use 1 minus x1 or 1 minus xt, right? So you can make a linear combination of these monomials, but then you expand it, right? Expand it, and then you can get some multilinear polynomials by using this way. There will be, of course, there may be cancellations and things like that. Anyway, so there's a polynomial that represents f, and the degree of this polynomial is the degree of the Boolean function. We write as a deg of f. And for graph H, we write delta g as a maximum degree of vertices in H. Now here's two theorems. So one theorem by Nissan and Szekedy in 94. They proved that block sensitivity is at most twice degree squared. And then there is another theorem by Gatzman and Lineal, which is actually a key thing. The following are equivalent for any increasing function. So the first one is for every induced subgraph H of Qn with the number of vertices not equal to 2 to the n-1, delta of H is bigger than some function Hn, or delta of the complement of H. So the not the complement, delta of Q to the n minus V of H is bigger than Hn. Or for any Boolean function f of s of f is at least h of degree f, right? So this allows us to reduce the problem to a problem on the induced subgraph of a cube. Why? Because if we find some function h that satisfies this condition, so whenever I take induced subgraph of the cube with the number of vertices not exactly half of the number of vertices of Qn, if this is the case, then for any Boolean function f, s of f is at least h of the degree of the polynomial. But degree is larger than block sensitivity. So if we have such a function h, then what we have, so degree of f is like, let me say this way, then block sensitivity of f is twice degree of f squares, which is twice h inverse sf. Okay, so the block sensitivity is bounded by some function of sensitivity, right? So this will allow us to prove the sensitivity conjecture if h inverse is a polynomial. Now I'm not going to show you the proof of any of these reductions. We are interested in the combinatorial part of the proof. So here's a theorem by Huang, which was immediately popular on the internet, and it became it was published in Annals of Mathematics very soon. You can find an article about this. So H is induced subgraph of G, no, not G, Q to the n, right? The cube with the V of H, number of vertices is 2 to the n minus 1 plus 1, so you just have one more. Then the maximum degree of H is at least the square root of n. And this is tied. But I'm not going to show you why it's tied, but you can think of it. So I will show you how to prove it. And there's a really nice idea. So here's a lemma. So let's A1 be this matrix 0, 1, 1, 0, and AN be the matrix block matrix obtained by AN minus 1, I, and minus AN minus 1. Okay. Now, then AN is a 2 to the n times 2 to the n matrix, real symmetric matrix whose eigenvalues are square root n of multiplicity 2 to the minus 1 and minus square root of multiplicity 2 to the minus 1. This is a key thing. So let's first see why this is true. And the claim is an squared is n times I. So a1 squared is I, obviously, right? And an squared is an minus 1 I minus an minus 1 squared, right? So when you have is a minus 1 squared and an minus I squared plus I, right? So you multiply this, and then an minus 1 minus an minus 1, and an minus 1 minus an minus 1, and minus an minus 1 squared. No, I minus an minus 1 squared. Oh, plus. Right. So what you get is, and I know by induction that this is n minus 1 I plus I, and 0, 0, n minus 1 I plus I. So this is ni. Alright? So why is this useful? If lambda is an eigenvalue of an, then an v is lambda v for the corresponding eigenvector. Right? But then an squared v is an lambda v, which is lambda square v, right? So this implies that, but an squared is n times v, so lambda squared is n, so that means lambda squared n plus minus, but the trace of an is going to be trace of an minus 1 twice trace of an minus 1, and inductively this will become 2 to the n times trace of a1, 2 to the n minus 1 times trace of a1, which is 0. So I know that every eigenvalue is either plus root n or minus root n, but sum of the eigenvalue, which is equal to trace, sum of the eigenvalue is equal to 0. So that means half of the eigenvalue are square root n, and another half are minus square root n. And number of eigenvalues are 2 to the n minus 1, so 2 to the n minus 1 of them are square root n, 2 to the n minus 1 of them are minus square root of n, right? So that's the proof. Here's a, but why is this an interesting? What is an? Think of the cube. Now I look at the first floor and the second floor. Then if I have adjacency matrix for first floor, and adjacency matrix for second floor, and then between the first floor and second floor you have edges connecting the identical copies, right? And those edges are can be represented by the identity matrix here. So the adjacency matrix of the cube can be written like the adjacency matrix of the smaller cube together with the identity matrix here. And if you look at the construction of AN, this is really like the adjacency matrix of the cube, except you have a minus sign here. Right? So that's the only difference. And this makes the proof really great because of this negative sign, you make this eigenvalue, the proof of eigenvalue very neat. Right? Now, we need one more lemma about the eigenvalues and maximum degree. Okay, so let H be an M vertex graph, and let A be a real, I mean, I have to say real, a symmetric M by M matrix such that okay, let me write Aij. Okay, that would be let Aij M by M matrix. Aij is non, so I always want to make sure that Aij is a plus minus 1 or 0, and it's non-zero if and only if, okay, let's say this graph is one of the Vn, Vm. Vi is adjacent to Vj. Then we have non-zero values. Okay. So the difference between this matrix and the adjacency matrix is that in the adjacency matrix you only allow 0 and 1. Here you allow -1, even if they are adjacent. Right? So for edges you either put 1 or -1 depending on your choice. But even with this weaker matrix, we can prove something. Right? How do we prove something? So let lambda 1 be the largest eigenvalue of A. Okay. Then lambda 1 is a lower bound for the maximum degree. And the proof is a simple linear algebra. So let V be an eigenvector corresponding to lambda 1. Okay. And now we know that AV is equal to lambda 1V. Right? So by let us assume that V1, the absolute value of V1 is bigger than anything else for all I. Anyway, otherwise you swap I and J, or 1 and I, right? So that choose the maximum Vi and then call it V1. That's relabeling. Now, let's look at the lambda 1 V1, the product of that. That's AV1, no, AV, and then I look at the first coordinate because AV is equal to lambda 1V. So if I look at the first coordinate, I can say this way. I look at the first coordinate, then that's lambda 1 v1, but this is equal to AV, but that's equal to sum of AIJ, no, A1J and VJ, right? Now, I'm adding this over all J which is neighbor adjacent to 1, V1. And then AIJ and VJ, but AI, the absolute value of this is 1, so this is like degree of V1 times the upper bound is V1, right? And this is equal to lambda 1 times V1, right? So we conclude that lambda 1 is less, absolute value of lambda 1 is less than equal to degree of V1. And that's exactly what we want. And maximum, well, why? Because maximum degree is greater than or equal to the maximum degree of V1. Okay. Now, here's a proof of the sensitivity conjecture. Right. So let H be an induced subgraph. Right. So we are proving this theorem. So H be an induced subgraph with 2 of Q to the n with the 2 to the m minus 1 plus 1 vertices. All right. Now, then the largest lambda 1 over H. So this means largest eigenvalue of H is at most lambda 1 of Qn by interlacing theorem, but also at least lambda of 1 plus 2 to the m minus 1 2 to the n minus 2 to the m minus 1 plus 1, right? By the way, when I say lambda of something, right, so lambda L of Qn means that L's largest eigenvalue of Q to the n. And this is by Cauchy's interlacing theorem. Right, remember, let me show you again. The reason is, so you can think of the A as the m by n real symmetric matrix. Oh, wait, I shouldn't say Qn. Let me fix it. It's not Qn, it's An. And this H, instead of H, what we have is An induced on V of H. All right. All right. So if you look at this corollary, then in this case we have this principal m by n submatrix. So the i's largest eigenvalue and of this submatrix has this relation. So we have this kind of relations. So this means that lambda 1 of an vh is greater than the 2 to the n minus 1 largest eigenvalue of an. But remember, the eigenvalues of an's are half of them are 2 to square root n, half of them are minus square root n, and this is exactly half place, so it's square root n. So lambda 1 of an vh is square root n. This implies that by the previous lemma, delta of h is greater than or equal to square root n. Right, that proves the sensitivity conjectures. That proves this theorem, Huang's theorem, and as a corollary, we have BSF as a most twice, so H inverse, that's a square, so SF squared and a square and square, so it's 4. Right, so it's amazing proof. Instead of using a adjacency matrix, you now allow +1 and -1, and this makes eigenvalues so simple that it gives a proof. Okay, that's it.